So the gold standard for QTL analysis with this scan1 function is interval mapping with this EM algorithm. And it's usually pretty fast, but it is iterative. It takes some number of iterations at each location. And if you have reasonably dense markers and reasonably complete genotype data, you can mostly skip that and use, there's an approximation that just uses regression that is from a paper by Haley and Knott, 1992. There was another paper at the same time on the same method, but this paper is better written, and so pretty much everyone refers to the method as Haley-Knott regression.
That's the secret of simple interval mapping, right?
Right. Okay. So what Haley-Knott regression does is essentially takes the first half step of this EM algorithm. You start out with, you have a column of phenotypes, and then you have this matrix of QTL genotype probabilities. And what Haley-Knott regression does is basically do linear regression of the phenotypes on this matrix of genotype probabilities. It turns out to be identical to doing weighted averages, because these are all between 0 and 1. It's equivalent to just doing kind of the first half step of the EM algorithm. I take the probabilities I calculated, QTL genotype probabilities I calculated just using marker data, no phenotypes, and then take the weighted averages as my estimates of the phenotype means. And that's Haley-Knott regression. And it is because it's just one regression step, it's much faster than doing EM, meaning 7 times faster, say, if EM is going to take 7 iterations to converge. And for kind of modern genetic data where you have very dense markers that are mostly filled in, this will give you effectively the same answer. The way you do this in RQTL is in this call to scan1, one of the arguments is method. And if you do method equals HK in double quotes, it will do the genome scan with Haley-Knott regression. It'll do a genome scan by Haley-Knott regression, assign it to some object. I usually want that object to have a name that's somewhat different than I want a new object name. So I'll say out.hk. And, I can plot that result the same way. I can plot the two results together next to each other. I could do, just the 2 main chromosomes. Maybe give them different colors. Those colors were not really very obvious in this case, but oops. But they're really, in this case, really similar. My data are reasonably complete, and doing Haley-Knott regression versus doing interval mapping you know, you see very slight differences between the blue and the red. Of the blue is interval mapping and the red is Haley-Knott regression. They're very similar. The more dense your markers, the more complete the genotype information is, the more the two things will be identical. So, I mean, if I do scan one with just the cross object, no further arguments, it will do interval mapping by the EM algorithm. If I want Haley-Knott regression, I just do method equals HK, and it'll give me similar kind of results much faster. And this function for plotting LOD curves, I can give it up to 3 of these scan1 type outputs, and it'll put them all simultaneously. Another way to do it is to plot one of them. You know, so plot the results for the EM algorithm, and then add in the Haley-Knott regression afterwards. Say in red, just those 2 chromosomes. If I say add equals true, it'll overlay the second one on top of the first one. When you're plotting 2 things that are very similar, you can't really see the difference. Rather than plotting them over on top of each other, it's often better to plot the differences. And if I type out minus out HK, R will know that one is, you know, these are both scan1 type objects, and they're in the same, the same, genome. So it'll just subtract the LOD scores and give me the differences. And I can plot that. This is the difference between the LOD score from standard interval mapping and the LOD score from Haley-Knott regression. So it'll just subtract the LOD scores and plot those differences. But the default is to truncate everything at 0. I mean, or to have the y-axis limits end up at 0. But there's another argument, y-lim. So if I make the y-axis limits from -0.5 to 0.5 and have a plot of just the differences, the LOD score from EM algorithm minus the LOD score from Haley-Knott regression. You can see that it's never very big. -0.2 is the biggest difference, where in this case, Haley-Knott gave a bigger LOD score than EM. Where in this case, EM gave a bigger LOD score than Haley-Knott.
So would this be a way of looking at uncertainty in your markers?
I get. Is this a way of looking at uncertainty in your markers? Not a good one.
So would anybody ever actually do this in practice for looking at their own data, or is this more just to show an example of the difference?
It's more to show. I guess, if you have, if you had time and you want to know, and you might try multiple methods, and plotting the differences would be useful for seeing, are the methods giving you different results? Each of Haley-Knott and standard interval mapping can give you bad results in certain cases. Haley-Knott regression, this approach, fast, is really the, if you have a lot of missing data, it won't do as well as using the EM algorithm. The only place where it's really bad is if you've done selective genotyping. If, say, you phenotyped everyone and then you genotyped only the upper and lower 10% of individuals. So, everyone in the middle, say in the phenotype distribution, they didn't have any genotype information at all. Then when you do Haley-Knott regression, they're all basically given a quarter, a half, a quarter as their 3 probabilities, because you don't know anything about them otherwise, so you just call them all a quarter, a half, a quarter. And that turns out to have to result in hugely inflated LOD scores. So Haley-Knott regression, absolutely fabulous for kind of modern genotype data. If you have dense markers, use Haley-Knott regression, except if you've done any kind of selective genotyping, in which case stay away from Haley-Knott regression. It's usually bad. If, you know, turns out if you just throw out those individuals and pretend like you never saw them at all and just do the analysis with the extremes, Haley-Knott regression works perfectly fine then. But most of the time, my collaborators will genotype the extremes and then at selected markers add in a bunch of, fill in, genotypes for everyone else. And so you don't want to throw out those middle individuals, but you want to stay away from Haley-Knott regression in just that case. So I've shown you how to plot the results. I didn't show you how to get a summary of the results. If you type summary in one of these scan1 output objects, it'll find the single largest LOD score on each chromosome and just show for each chromosome the position at which the maximum LOD score occurred and that LOD score, and give you a marker name if that maximum occurred at a marker, or give you a cryptic name for a location if the maximum occurred at one of these pseudomarkers, or these filled in positions. The summary function takes another argument, threshold. If I put 3, say, it'll just give me, it'll for each chromosome find the location with the maximum LOD score, and then, but just print those rows that have LOD score bigger than that threshold. So it shows you chromosome 7 and 15, just those 2 LOD scores.
Is there a way you can see a LOD score for each marker, like for the curve itself?
Yes, if you just type the name, this is basically just a big rectangle that has chromosome, position, LOD score. So if you wanted, say, all the results for chromosome 7, you can subset that thing just like a data frame in R. So there's you could say, give me all the rows where the chromosome column is equal to 7, and it will spit all that out. Or you could just type it. Don't do this yourselves, because it may take forever with this system that we have. But if you just type it, it'll just spit it all out, and you could scroll back through there as you wish. You could also write it to a comma delimited file if you wanted. And it'll show up on my desktop over there if you want to look at it elsewhere. But because it's just chromosome, position, LOD score, and then the row names in that data frame are the marker names, or these names of these pseudomarkers. But we had 93 markers total in this data set, but we did these QTL calculations at 1,268 positions. So every centimorganal across the genome, including at the markers. So if I type summary and threshold equals 3, it gives me the chromosomes that have LOD score bigger than 3. And a key question is, how do I decide 3? And the best way to answer that is to do a permutation test, where we take our data is a set of genotypes and a column of phenotypes. Say markers here and individuals here. And so in deciding how to decide when the LOD scores are big enough that I can be confident that there's a QTL, what I want to know is if there were no association between genotype and phenotype, how big of LOD scores might I get? And so a permutation test, I shuffle this column, shuffle the phenotypes relative to the genotypes, do all these calculations, do a genome scan, calculate the LOD curves, and then find the maximum. And then I repeat that a bunch of times. And end up with some distribution of the genome-wide maximum LOD score across different possible permutations of the phenotypes relative to the genotype data. And I can then, this distribution will depend on what type of cross I did, a back cross versus an inner cross. It'll depend on the size of the genome, a genome like mouse versus a genome like fly. If I have a bigger genome, I'm maximizing this LOD score across more space. I'll tend to get bigger numbers. And so for the mouse, this distribution will be have considerably larger tail than for a fly that has just 3 little itty-bitty chromosomes. Versus wheat that everyone, I don't know how it is genetically, but in megabases it's much bigger than mouse. So how do we do this in R? It's a lot faster if we do Haley-Knott regression. So, doing the QTL analysis with the EM algorithm is not much, doesn't take much more time than Haley-Knott regression. But if you're going to do it 1,000 times, then it'll be 1,000 times that difference, which starts to get slow. So I'm going to use Haley-Knott regression to do these permutations. And to do the permutation test, we use the same scan1 function as we do to do the genome scan. We use all the same arguments that we would before. We just add one new one, which is n.perm equals some number of permutations to do. And this should take about 10 seconds on your computer, maybe. It took considerably less than 10 seconds here.
So the thresholds generated from Haley-Knott regression, would those be applicable to the EM thresholds? Can we do permutations with Haley-Knott and then go and do our final analysis with EM and their equivalents? For publication?
For publication, I would, if I'm going to present EM results, I would spend the time and do the calculations with EM. The EM algorithm and Haley-Knott regression will give you somewhat different results, and those results may be even more apparent when you do it across many permutations. So it's better to stick with the same method when you're doing the permutations. So the output of this, in this case, is just a single column with the genome-wide maximum LOD score in each of those 1,000 permutation replicates. If I type that name, it'll show me those 1,000 results if I wanted to. If I type plot, if I say plot that thing, it'll give me a histogram of across those 1,000 permutations, the genome-wide maximum LOD score. So the 5th percentile is like around 3.5. I mean, the 95th percentile is probably around 3.5. And the biggest one observed at all is maybe about 5.7 or something. If I type summary O-perm HK, it'll give me a couple of significance thresholds. So the default is to give you the 5th and the 10%. It'll give you the 95th quantile and the 90th percentile. If I want other ones, I think I give alpha here, 0.05 and say 0.063. If I wanted the 63% significance, I can get that threshold by giving this summary function for the permutation test, this argument alpha for the kind of type 1 error rate. And I can also use these in the summary function for the scan 1 result. If I just type scan 1 out.hk, it'll give me the single, the maximum LOD score on each chromosome and tell me where it occurred. If I give it these permutation results and also give it some significance level, it'll calculate the threshold for me and just show me those chromosomes that had a LOD score bigger than that threshold. If there's another argument, p-values equals true, it'll calculate that threshold, show me just those chromosomes, and then also give me my estimate of the p-value for that corresponding to that LOD score, which is the proportion of the 1,000 permutations that had a LOD score of 6.11 or better, the proportion of the permutations that had a LOD score of 5.3 or bigger. So 0 and 1 in 1,000. For scan 1 permutations, if you're on a computer that has multiple processors, there's another argument, n.cluster, that will try to, don't try this on your computer in front of you now, because we don't know what might happen, but that can light up all the processors on your computer at once and make it go faster. You see, on my computer, up here is telling me how much of my CPU I'm using. And so now it's, intensely heating up this laptop doing 20,000 permutations sort of all at once. And it didn't take very long. I got the fan going, but there's a neat trick in for Haley-Knott regression in this context that I can create 20,000 permuted versions of my phenotype as a big matrix. That I permute the phenotype and then I do it 20,000 times and make a big permutation matrix. And then when I'm doing the regression, when you're doing a regression, you can regress a whole bunch of phenotypes sort of all at once, fast. Because the main part of regression is I'm taking this X matrix, which are the genotype probabilities at a given position, and calculating X prime X inverse X prime Y. And I can replace the Y column with a big Y matrix and then do all the permutation calculations at once. There's some trade-off between how big of a matrix I use versus doing it a bunch of different times. But I can do, I mean, with Haley-Knott regression, we can do a lot of permutations quite fast for a data set of this size. And the answers are not really any different. They're just more precise. So if I do 20,000 permutations, then I call this summary function, give it the permutation results, say significance level 5%, and give me the p-values. I now find that for this first locus I had 2 in 10,000, so maybe 4 in 20,000, I guess. Is that right? And but I still have, this is really small and this is really small, but it's like 1%. It's just a more precise 1%. I mean, 0.1% is a p-value. Yeah.
Do you have to do all the phenotypes you have? Do you have to loop, just do a for loop for each phenotype, or is there a way to put in a command to, like, slice an array to do a certain number of phenotypes?
The question, just for the permutation part, if you have multiple phenotypes, you need to do separate permutation calculations for each. And one way to do it is to do them one at a time. Do the permutations for one and then the permutations from another. Another way is to, permute the whole phenotype matrix and do the genome scan and write down the maximum for each of those phenotypes and then repeat that 1,000 times. So either kind of fill out this matrix of maximum LOD scores for permutations by phenotypes, either one column at a time or one row at a time. For some cases, when you have correlated phenotypes, you really want the permutations for the different phenotypes to be paired. You want to use exactly the same permutations so that the permuted phenotypes maintain that correlation rather than permute each column totally independently. This is maybe but you can do either way. It is going to be slower. Some of that you might want to just do by hand. You can, use your own special tricks to try to speed it up. And maybe this is maybe a good time to point out that this data set has 4 phenotypes really: blood pressure, heart rate, body weight, heart weight. That's what those are. We've just been studying blood pressure. You notice I haven't said anything to it about which phenotype to use. Scan 1 is the one that cares, and just by default it just uses the first one. If I wanted to do scan 1, if I wanted to do a genome scan for heart rate, I need to tell it to use a phenotype column other than the first one. So I can either say use the second column, or I can give it the precise name that I want, heart rate. And maybe I'll just stick with Haley-Knott regression. So if I want to do a genome scan with a phenotype other than the first, I have to use this pheno.call argument to scan 1. And so then, and I can plot that with the results of, for blood pressure. So the LOD curves that we saw before for blood pressure are in blue, and the LOD curves for heart rate are in red. It sort of looks like the locus on chromosome 15 that's affecting blood pressure is also, looks like it may also be affecting heart rate. I don't see the same kind of effect on heart rate on chromosome 7, but I see another QTL on chromosome 2. Seeing that large effect QTL on heart rate on chromosome 2 and noticing that there's a blip there on chromosome 2 as well for blood pressure, I'd be inclined to think that maybe there's a QTL for blood pressure on chromosome 2 at that location as well. I'm pretty sure that's real. These things are correlated. This one here in blue for blood pressure looks more interesting to me than, say, chromosome 8. Even though their LOD scores are the same. I would, I could be wrong, but I'd be interested, I'd be a bit more interested about chromosome 2 for blood pressure because of this correlated trait having a locus there.